This is the answer to Chapter 2, problem number 59 from the Smith Organic Chemistry textbook. And in this problem, we're asked to consider ethyl butanoate, which looks like this. Okay, so there's ethyl butanoate. And we are asked which hydrogen is most readily removed when ethyl butanoate is treated with base. Propose a reason for the choice, and using data in Appendix A, estimate its pKa. And so remember that the most acidic hydrogen, so remember that a stronger acid is correlated with a more stable conjugate base. So when we are looking at this molecule and thinking which hydrogen is going to be most acidic, we could think, for example, uh, if we remove one of these hydrogens, are there any that are going to be extra stable to remove? And so there are two hydrogens here on this carbon. And if we were to remove one of them, so like this, we'll just say base. So if we were to remove one of these hydrogens, we would get a resonance stabilized conjugate base. So down to one hydrogen, and then also a lone pair and a negative charge. And so what can happen is the lone pair can add in here to form a carbon-carbon double bond. And these electrons can kick up to this oxygen, and I'll put the oxygen's lone pairs on it. And so we can draw a resonance structure for this conjugate base that looks like this. And so this is a pretty good resonance structure. I've talked before a little bit about how it's best to try to seat a charge on an electronegative atom. And so in this second resonance structure here, we have our negative charge seated on an oxygen, which is electronegative. And so that's a strong resonance structure. So that's going to contribute a lot to the resonance hybrid. And basically, it's going to make this conjugate base extra stable. And only one of the two hydrogens on that carbon, only removing one of them, has this potential resonance structure. There's no other carbon in this, or pardon me, no other hydrogen in this molecule that could be removed that would give us a comparably stable conjugate base. And so one of those hydrogens is definitely going to be the most acidic. So in terms of estimating the pKa, using Appendix A as the problem instructs us. So in Appendix A, ethyl butanoate is not in there, but it looks like ethyl ethanoate is, and so ethyl ethanoate would be like this. So that's ethyl ethanoate, and we can estimate that these hydrogens here on this carbon are probably going to be comparably acidic to the ones in ethyl butanoate. And so let's see, the pKa of ethyl ethanoate in Appendix A is 24.5. And so for ethyl butanoate, we can say around 25. So again, over here, this is 24.5. And so we can call ethyl butanoate about 25. And so that's how to approach this problem. So to determine the pKa, we just need to look for the closest molecule that we can find in the appendix. And then to determine which hydrogen is most easily removed, we need to consider the stability of what the conjugate base would be in each case. And in this case, in this instance, there's clearly a best stabilized conjugate base. And so that's the answer to chapter 2, problem number 59.